Hello, today we'll be talking about networking plus Wireshark. This session is presented by Michał and Matthew. First, we're gonna start with private IP ranges. We have three classes of IP ranges, A, B, and C. 10.0.0.0 to 10.255 three times is class A, second one is class B, third one is class C. Class A is most likely to be used by ISPs, class B is by the medium to big organizations, and Class C is most likely to be seen at your home network. When you send a packet, it uses two protocols, either TCP, which is very slow but it's stable. It always asks whether the packet was received, and then the server answers whether it was or not, or UDP. UDP is very fast, but some packets get lost, some packets are too slow, so they never get there, so you just send another one. You can see this diagram, the difference between the TCP and UDP. As you can see, the header size, so the amount of data that's being sent in TCP is way bigger than in UDP. It's the speed is astronomically different, and it's used for various different protocols. For example, UDP, you would be watching a movie. In TCP, you would be sending an email. But let's assume that we're gonna watch a movie with a TCP protocol. Why would that be bad? Well, first of all, yeah, it is slow, but so what? We don't care. We want to see all the pixels, right? But then there is one problem. If one pixel doesn't load, then you can't watch the whole movie. You have to wait for like a second or two because of one pixel. Imagine doing that over and over and over again. Suddenly you have a problem. With UDP, that's never a problem. You just lost one or two pixels? Meh, what's the problem? TCP follows a strict routine of how to authenticate. So when you start a TCP connection, you first send a synchronized packet. So let's say this is Perry's server and Perry wants to say hi to Harlan. So to start, before he even sends the data, he has to send the synchronization packet. Han has to acknowledge it by saying synchronize and acknowledged, and then Perry says, oh yes, acknowledged. And then he can send the data. Uh, due to the due to the amount of years that passed, it used to be sing and act that there were different packets, but nowadays you most likely see them as a one packet. Now let's start with HTTP status codes. When you get a website, for example, let's say you wanna load a liverpool.ac.uk website, you have different status codes. Those are 200 if you got the website successfully, 300 although this is not seen here, that means redirected, and 400 which means something went wrong. It's most likely on your fault because let's say the packet was too big or the packet is empty or some problem on your end. 500 if it's a problem on the server end though. As you can see, there are different codes at the end of it. They all have different meanings, but most the most important is the first number, not the last. As you can see here, we are sending data in plaintext HTTP. So this is a header in red. You can see everything your browser sent. So in this case, I just want to request caterpillars.myspecies.info website, and I just want to see the index page, the main page of the internet. And the server responded with 200 saying, yeah, you can get it. It's for you to take. And here we can see all the data. But notice that we send them a header and it responded with a header and then body. However, there is also HTTPS. So in the same example you saw here, you can read the body. In here, you cannot see anything. You don't know what's happening. For example, this is a Google. You cannot read it. But imagine if you send password and login over this HTTP rather than HTTPS. You can read this. As long as you're on the same network, you can see the data. For Also, for example, here we have FTP. This works in plain text, meaning that if you have a user or password, you can read it. If you, for example, connect to FTP server, you can read everything that was sent over. You can only read it if you're on the same network due to how networks work. However, you can read everything, every command that was executed by the user. This could be done with browser, this could be done with FTP client. It's all readable as long as you're on the same network running a Wireshark, which is obviously could be used for malicious purposes. Now I'm going to show you how to extract objects in Wireshark. So in this example, I'm going to load this website. And as you can see, I just did some requests, and it's been more than one request. To export objects, you first you will first want to stop the Wireshark from working, and then File, Export Objects, and the protocol which you use, in this case HTTP. Then you're gonna find the picture in this case. I've called it AA. Here we go. I've loaded a picture. Let's see if that picture is somewhere on this website. Here we go. This picture, this website was loaded in HTTP, so it's unsecure, all in clear text. What we just did, we just downloaded the picture from the networking information that we found. This could be done on my network. So for example, let's say my brother is on the same network and he has run a HTTP website and he logged into some website. Suddenly I can see his login, password, pictures he downloaded, whatever he loaded. Let's go back to the presentation. Another thing that you can do is follow the stream. So for example, in this case, if I right click this first packet and click follow and HTTP stream, you're gonna notice that now I can see everything that happened. So I've sent the header, server responded with header and the body. In this case, I've only loaded one page, but if we assume that we loaded 50 HTTP pages, suddenly following the data is very important. It can become very useful, especially when doing CTF challenges. On this page, you can see different rules. So for example, you see this. This is clear text. This is HTTP data, right? So this, so on this page, you can see the different protocols that are being used and how do they react. For example, here you can see the bad request. Here you can see the reset request. So for example, let's say I loaded a website, but I didn't fully load it. So for example, I just loaded it, but I just clicked stop. That would send a reset. If we try to find it, here we go. It screwed up. What you might also notice is that Wireshark supports filters. So in this case, you could do something like, I just want to see HTTP, and you're gonna see it. You can say, I just want to see TCP packets. You're gonna see it. You might want to say, I just want to see UDP. This is very useful. But what you can also do is HTTP dot. And for example, in this case, I just want to see everything that a server screwed up. So the server said, hey, I screwed up, nothing. But what you could do is Change it to 100, and let's see. Yes, we got something. There are different comparison operators. For example, it's like programming, honestly. For example, equal sign. You can see if the response is 200, so if it got there. Yeah. If you don't understand it, I recommend you see the website that's in the dark link. Thank you.
So once we've learned about TCP and how it establishes its connections using sync and acknowledge, we can basically move on and start using a tool known as Mmap, which is basically just a port scanner that can scan servers and devices. It's used for discovery. There's a load of commands which you can see here on the right. This is if you do dash dash help in terminal. And if you really want to learn about Nmap, I recommend reading the manual for it by doing man nmap, or you can find it online. With CTFs, the most important ones will be the ones such as dash P. This lets you run specific ports, or you can do it for all ports if you do dash P dash. There's a range about between T0 and T5, and this is dependent on how long you want to wait for a response from the host. Normally they call T5 insane mode because the waiting response is extremely short, and this normally creates a lot of noise, but it's quite effective and quick. Stealth scans are useful because they end with an RST, which basically means that they don't complete the TCP connection, and this is great for non-discovery. Dash F lets you scan the most common ports on a server. Dash dash script lets you discover and use different scripts, such as vulnerability scripts. Dash PN lets you discover hosts without pinging them. And dash SV is quite useful for finding different services and OS detection. So what you're about to see is in the next slide. Here we can see that we've done a successful scan. We've done an Nmap scan for all ports using the dash p dash, and we've applied the T5 insane mode on this router, which has helped us lower the length of time we have to wait. We can see the latency, and we can see how many filtered ports we have. Additionally, Nmap has returned all the ports which are open on this device. The services for the ports are shown by looking through Nmap's database, which is about 2,200 known ports, which it can identify what they're being used for. However, as we can see, the bottom two are unknown ports, which means they're not registered in the database. Most of the time, these are just a lot of open ports that you don't really need to worry about. They don't really lead anywhere, so I wouldn't be too concerned. Normally, you want to be looking for ones like SSH ones, which is port 22. It's not currently shown here. And also we can see that there's one current host active.